Hello, good evening. Can you hear me and can you see my screen?
Yes, sir. Yes, sir.
Okay, we'll start at 7:05. Let some other people join. Okay, we'll start. So last class we looked into rotating magnetic field, mostly of induction motor. As I said, they are same for induction and synchronous machines. So synchronous speed, uh, relative speed between stator and rotor magnetic fields, slip and all we have discussed, and effect of the speed on the rotor induced voltage. That is nothing but Faraday's law we discussed last day. Today we will delve into induction machine in detail, means just solving the problems. So yeah, this is the 6th week of the course Electric Machines 2, which is instructed by Professor Tapasya Bhattacharya from IIT Kharagpur. And I take this doubt clearing class every week, Monday, 7 to 9 p.m. I am Saptarshide. I am a PhD scholar at IIT Bombay. So as usual, we'll start first by taking doubts from your side from this week or last week's lectures. Then we will look into solving the problems. Okay, no doubt. So just one remarkable feature of induction motor, you will see that induction motor is nothing but a transformer. Can you just confirm once that you can hear me? I'm talking for quite a long time now.
Yes, sir, it is audible.
Okay. And you can see my screen also, right?
Yes, yes.
Okay. So induction motor is nothing but a transformer by principle. But there is something that is vastly different between a transformer and an induction motor. The first thing that is coming to your mind is might be transformer does not rotate, but induction motor rotates. Yes, that is true. But there is a result or outcome of that phenomena. Thing is, say for example, we take a two-winding transformer, as I'm drawing here. Now, you have some voltage source here. You can have some load here. You can have another source here, whatever. But fundamentally, what we have is the frequency on both the sides must be the same. If you simply take this circuit, say one AC voltage source feeding to another AC voltage source, which is our typical power system circuits, or maybe an inverter feeding the grid, whatever, E1, E2. The condition for non-zero average power flow is that frequencies must be the same. Frequencies must be the same. Otherwise, there will be pulsating power flowing, but you will not get any non-zero power, non-zero average power. See, last day we discussed something about electric machine. That is, if you look at the magnetic fields, of the stator and the rotor from a given reference frame, that can be anything. That may be the stator, that may be the rotor, that may be the synchronously rotating reference frame, that may be any other randomly rotating reference frame, whatever. But if you look at the stator and rotor magnetic field, you will see that they are static with respect to each other, or in other words, um, their relative speed is zero. Then only non-zero average torque is possible. You see, this frequency is also the same thing. If you do not have E1 and E2, so I wrote E. If you draw E1 and E2 with respect to time, if you try to draw, just imagine the frequency are not same. If the frequencies are not same, what you will see is, say for example, you are seeing them on an oscilloscope. This one is moving away continuously. Frequency is different. There is no constant phase difference. So here also the same thing. For a constant power flow, these two waveforms must be static with respect to each other. Then only there will be a power flow. So this is easily understandable in power electronics, but the problem, in transformer. But the problem is with induction motor. Induction motor, stator, that is connected to the, say, grid connected induction motor to the grid. So it is running, the stator circuit is working at grid frequency, let us say 50 Hertz. Whereas the rotor, when it is rotating, it has some other frequency, some other operating frequency, which is SF. So two electrical circuits operating at different frequencies, and there is power flow between them. So the problem appears when we are trying to derive an equivalent circuit for the induction motor. Physically, we can understand that is there is power flow. But when you're trying to draw an equivalent circuit, electric circuit, definitely you cannot have two circuits operating at different frequencies. Then there will be no power flow. Then how at all is it possible to draw the equivalent circuit of induction machine? Frequencies are different in the two circuits. So now, by some way, we have to connect the stator and the rotor circuits. So how does the rotor circuit actually look? It is like this, right? There are either windings or squirrel cage which are short circuited. So definitely it looks like this, short circuited RL circuit. And there is some induced voltage, E rotor, let us say. R2, X2, these are constants. And the frequency of this E rotor is SF. Also, the magnitude ER, this is equal to, let us say, some standstill value E2. So this at standstill. Right? Now, when it is rotating, this becomes AC2. At standstill condition, what happens? Slip equal, CP is equal to 1. So we can just say ER is equal to AC2. And since the circuit frequency is changing, X2 cannot be constant. L2 is constant. X2 cannot be constant because that is F omega L2. One frequency term is there. So there should also be a slip term. So the rotor circuit is like this actually. Right? Now if we write the equation, say one current I2 is flowing, I2 is AC2 by square root of R2 squared plus SX2 squared. Now this expression is manipulated as E2 by R2 by S whole squared plus X2. Now see, if instead of this circuit that I have marked as 1, instead of this circuit, if I have a rotor circuit like this, then it is equivalent. It is equivalent. And at the same time, you cannot claim that this circuit changes or this circuit is frequency dependent. Why can you not claim? Because the voltage is not changing. The inductive reactance is not changing. Only thing is the resistance is changing with speed. So whatever standstill voltage E2 was there, that is still the same even with change in speed. Hence, the operating frequency is also fixed. Now we can connect this circuit with the stator equivalent circuit because their frequency is now same, frequencies are now same, and hence non-zero average power flow is possible. Is it clear up to this? So this is something that is sometimes overlooked. Now from here, some very basic equations of induction machine are derived. That is PG, which is called gap power. Gap power is how much power is crossing the gap. Okay, basically how much power is going to the rotor. So how much power is going to the rotor? Some power is entering to the stator, some power is lost um, in the stator resistance. So input power minus stator resistance loss is the gap power. Now if you look, so we are talking about rotor. So now just look into this side. So here PG is entering, and that is causing some current I2 to flow. Now I can definitely write PG is equal to I2 square times R2 by S, because that is the only element that can dissipate power in the circuit. At the same time, now you think about from the actual perspective of the induction machine, R2 does not change. This R2 by S, we can write as R2 plus 1 by S minus 1. This first component R2, rotor resistance, that does not change. So definitely I2 squared R2 is the rotor copper loss. So this is equal to slip times gap power. And the rest of the gap power that is what is called the gross mechanical power So this is the mechanical power that we get from that the rotor develops. Now from here, two losses go out. One that goes out is core loss. Another one that goes out is the friction and windage loss. After this, what is remaining is what we actually get at the shaft. This is the output mechanical power, which is also sometimes referred to as BHP, brake horsepower. This BHP is actually the rating of the motor. So if there is a motor, induction motor, any motor rated for say 5 kilowatt, that means you are getting 5 kilowatt at the output from the shaft, and the input power is more than 5 kilowatt. How much is it? It is 5 by eta. Eta is efficiency. This is the input power. So motor rating is always the output rating. Same for generator also. Output electrical power, whatever you get, that is the rated power. So any doubt in all these discussions?
No, sir.
Okay, then we'll go into the problem. So this is the equivalent circuit of one induction motor. Per phase equivalent circuit. per phase, and they have mentioned standstill equivalent circuit. Refer to the stator of a 3-phase 4-pole 200 volt. It's a very bad practice. I don't know why they do this line to line voltage. See, even if it is not written, or if nothing is written 200 volt, if there is a rating of 3-phase supply, voltage rating is always line to line. Voltage rating is always line to line. There is no space for confusion here. Okay, 50 hertz star connected induction motor. Motor is running at 5% slip. Friction loss is given. Estimate the line current drawn. Okay. So now this is the standstill equivalent circuit. If we draw the equivalent circuit and it is rotating, everything is same, just the resistance. It becomes R2 by S. Rest are same. Now 200 volt is line to line voltage, and it's star connected induction machine like this. Star connected. So phase voltage will be 200 by root 3. Volt is here. We have to find out the line current. So now all we have to do is just solve this circuit. What we have is 0.16 plus J 2.5. This is in series with this parallel combination, which is J 100 magnetization branch and parallel to the rotor circuit 0.25 by 5%, 0.05 plus J 1. So this is the equivalent, equivalent inductance, equivalent impedance at 5% slip. Now you can use calculators and all to find out this. You can do hand calculation also, whatever. The final answer that will come out of this is 5.05 plus J 3.73 ohm. Okay. So then what will be the line current? Line current will be simply 200 by root 3 by the magnitude of J. Magnitude of J is this will give you some 18.38 ampere. So just the calculations here. Only thing to note in this problem is that the given one is a standstill equivalent circuit. So you have to incorporate this. So here what we had is the first term is the rotor loss. The power lost in the rotor circuit is also called the slip power. And this is the mechanical power. So it is like there is a resistance of this value 1 by S minus R 1 times R2, and a current flows through this. I2 current flows through this resistance, and there is some dissipation of heat in the equivalent circuit. So that dissipation is nothing but the mechanical power in the actual machine. Okay. You go to the next question. Estimate the input power. So line current we know. So input power is √3 times, just a second. Okay, one thing I forgot here. This is PG. There should be a 3 times if three-phase induction machine. The whole gap power, when it flows through the gap, there is nothing called phase. It is flowing to the gap. 3 times. 3-phase induction machine. Anyway, so input power is √3 VLIL cos phi. VL 200 volt. IL we found out. What will be the cos phi? Cos phi is the power factor angle. So that will come from here. This will decide the power factor. This will decide the power factor. So if current is flowing like this, then this is IR. This is JIX, the total current, the voltage, the current, this angle theta. So tan theta is X by R. X by R. So from here, if you find out, theta will come out as 36 degree. So these times cos √3 VLIL cos phi, that gives you the power. Now one thing is here, no, this gives us three-phase power because √3 VLIL cos phi is the equation for three-phase power. Or else you can do like this, same thing, one phase into 3. It gives you the same thing. So the power comes out to be 5122.96 watt. Okay. Estimate the speed in RPM. Sleep is given. What is the synchronous speed? 4-pole 50 Hertz. 4-pole 50 Hertz is 1500 RPM. 2-pole is 3000, 4-pole 1500. So speed of the rotor is 1 minus S times 1500 RPM. S is given as 5%. So 95% of this, which is 1425 RPM. Estimate the gap power, PG. So we have to first find out what is the rotor. So total rotor copper loss is 3 times 3 phases I squared R times what is R 0.25. How much is it? What, and we have seen that SPG is the rotor copper loss. So this is equal to SPG. So PG is that divided by S, which comes out to be 5067.
Sir, one small doubt.
Yeah.
Here, 18.38 is the total current run from the supply. Sir, it is not flows through the rotor. Rotor current is different. I think.
Oh yes, true, true. Yes, this is not this
Sure.
current, sorry. We have to do from the input side. Yeah.
The rotor current, like we have to, I is given, we have to find out I1, I2.
Yes, we have to find out the branch currents. That is one way you can do, or we can do it in an easier way. Since we have the input power, gap power is simply, sorry, I did it wrong. Input power minus stator copper loss. So input power we just saw 5122.96 minus 3 times, as correctly pointed out by him, this one is the one that is flowing to the stator resistance of 0.16 ohm. So 3 times 0.16 times 18.38 squared. Four nine six zero. The other way is to solve the circuit even more and find out the branch currents, how much current is flowing here, how much is flowing here, then find out the rotor losses and all. But this is easier, much easier. Okay. Now gross mechanical power, that is 1 minus SPG. So 95% of this, 4712 watt. Shaft power or output power is the gross mechanical power minus the friction loss, which is given as 1200 watt. So it comes out 3512 watt. and shaft torque. So power is the torque times speed. So shaft torque is power 3512 by speed we have found out 1425 rpm. This has to be converted to radian per second SI unit. So this is revolutions per minute, revolutions, radians per minute, radians per second. This will give you some 23.5 Newton meter. And then finally efficiency we have input power, we have output power. So it's output by input power. .5%. Okay. This thing I did a mistake here, so be careful. It's better to have the circuit in front of your eyes. This is the current, not this one. Now we can easily find out the current, the rotor current if we want to, because we know the rotor power loss. SPG is the rotor power loss, and that is the this I2 squared times R. So from here you can find out I2 rotor current. Okay, then we'll go to the next question. Three-phase 10-pole 50 Hz induction motor, star connected rotor, per phase standstill resistance 0.4. And reactance of this much. When the stator is excited with the rated supply, a standstill EMF 160 volt per phase is induced. Estimate rotor current at starting. So at starting, the circuit looks like this. Starting means standstill, zero speed, 160 volt. So what is the current? So I2 at starting, simply 160 by square root of this plus this. And this will give some 65.75 ampere of current. Okay, power factor. So power factor is simply cos theta. Cos theta is R by Z. R by Z is a very low power factor starting. Next is torque at starting. So you have to find out mechanical power. Mechanical power is 1 minus S times PG. Just a minute. This gives PM 0. PM cannot be 0. Okay, power has to be 0 because the speed is 0. You cannot do it from here. You got the point, no? I was trying to find out it from here, but still at standstill, the machine speed is 0. There is non-zero torque. But since the speed is 0, the power is 0. You cannot get it from here. From power point of view, you cannot get the torque. To get it some other way.
So 3 times I2 square R2. No?
Yes, that is the that is the rotor copper loss. So
S is 1 at the starting.
yeah, 3 times there is 0.4 times current squared. Rotor copper loss is this 5189.19 watt. Now rotor copper loss just a second, I have a doubt. Just a minute. What we have is this is R2. This is 1 by S minus 1 times R2. Now at starting, this one is actually shorted 0. So this is the gap power at starting. Then how do we get the torque, starting torque?
Is that from the gap power itself we can find the torque, sir? Torque is equal to the gap power divided by the omega. That is the synchronous speed we can consider.
Yes, yes, sir.
The only thing I can see here. So synchronous speed, it's 1500. Is it 4 pole?
Yes, sir. Yes.
No, 10 pole.
10 pole, 10 pole.
So 10 pole is wait, I'm doing mistakes. 20F by P.
600.
600 RPM.
PG by 2 pi.
So this will be
2 pi by 60. Yeah.
how much is it coming? I think I'm missing something here. Some 82.
And the procedure is correct, sir. I think.
So this by synchronous speed. Why is it synchronous speed? I'm getting a confusion here.
In the air gap, the rotating magnetic field is rotating with synchronous speed. We are considering the air gap power. There, we should have to consider the speed as synchronous speed. We can get the torque equation if you can compare with
Yeah, I think, okay, we'll some other torque equation is there. I think it comes from there itself.
yes, sir. Yes, sir. Same. If you can compare with this PC by 2 pi ns here, sir. Their other one is called PM by 2 pi n. That is NR. Same. We can get
Yes,
the final relations
same
are
thing.
same if you can compare.
Yeah. We're having some. Anyway, we'll go forward. So find the rotor current at the speed of 588 RPM. What was the so? No, everything is just solving the circuit. We will not consider any change in E. We will take that E remains the same 160 volt. E remains same at 160 volt. X remains same. R changes. That's how we will tackle the change in speed. Okay, so every time you have to find out the slip. Slip is 588 600, that is 12 by 600 1 by 50, 0.02% slip. Now rotor current, so rotor current at this speed will be, voltage remains same, x2, where is x2, 2.4, 4 squared plus R is how much? 0.4. So this is the rotor current at this speed. This will come out to be some 7.94 ampere. Okay. Now the torque at the speed of this. So what we can do is air gap power we can find out. Air gap power is 3 times I squared R I squared R R2 by S actually 0. No, sorry, air gap power. Yes, air gap power is R2 by S 0.4 by 0.02. That is 3782 watt. Now mechanical power we derived 1 minus S times Pg. So this times answer times 98%, 1 minus S 0.98, that is 3706 watt. (3706 watt), and hence the torque that we are getting is 3706 by is 588 times 2 pi by 60. No, 60.2 Newton meter.
Yes, sir. Same, exactly same formula. Yes.
Yes, so this is why we cannot do it in no load using that formula. So this is what comes to our rescue. I forgot. I studied long back. Thank you. Okay. We have 2 more questions left for today. So now we add external resistors of 2 ohm per phase to the rotor. We know that rotor resistance control is something that is used for increasing starting torque. This is done to increase the starting torque. So you would expect an increase in starting torque. Let us see what happens. So now our equation looks, sorry, our circuit looks like this. So resistance is now how much? 2.4 ohm. And this is J2.4. Rotor current at starting. So again 160 volt here. So rotor current at starting will be 160 by square root of this will give 47.1 ampere. And starting torque, then we will find out gap power. Gap power is I squared R, 3-phase. This is this much, then the torque is Pg by synchronous speed. (600 RPM). So
The power is some 159, sir.
what? 159.
72.
Oh, sorry. There's a mistake here. One digit I missed, I think. 5. No, I don't know. 15972.55.
Yes, yes.
So this divided by 600 times 2 pi by 60. 250 Newton meter. 254.2. So without the resistance, we had a starting torque of 82 Newton meter.
No, 60, I think.
Now it is 250.
Yeah.
Some more thing we can do a little bit just to get an idea of the power factor. What happens to the power factor? That is, say for example, if we find out the power factor, say at 588 RPM, what the power factor was, if we find out. Rotor power factor only, because other data we don't have at our disposal. And with blue. Then it is just the resistance divided by impedance, total impedance. So R2 by S, how much was R2 by S? 0.04 by 0.4 by 0.02 by the total 0.4 by 0.02 squared plus 2.4 squared. This will give you good power factor. Now you think about the starting power factor with, just to have a comparative idea, with this rotor resistance. If you do starting power factor, you will get here something like which is 2.4 comes out, gets cancelled, 1 by 1 plus 1, 1 by 2, yes. So although the resistance is quite high, the power factor is low. That is because the slip, there was some slip. So just to give you one idea, like this, I do not know how to what to say, how to look into it. See, for DC machine, this is very easy, very easily understandable, that you have, say, a DC motor. If you consider, say, you have a back EMF like this, E, some current I is flowing, and you have a supply voltage V, and the current I is given by V minus E by R. Right. Now, when you load the machine, the speed reduces. Speed reduces means E reduces and I increases. The back EMF reduces. The same thing is for induction machine also. The back EMF here is generated in this fashion. Or let me draw one resistance only. R by S. Now, S is omega S minus omega R by omega S. So when you load the machine, speed reduces, omega reduces, means S increases. S increases means R by S reduces. So the equivalent Z, that reduces. That is why for the same voltage, the machine draws more current. This is how I try to get the physical idea why the current increases when you load the induction machine. And if you are if the machine is at standstill, that means two resistances, one is R, another one is 1 by S minus 1 times R. This one becomes 0 at standstill. That is why the standstill state test is also called short circuit test of induction machine. Principles are same as transformer. Principles are same as transformer. Okay, so that's all for today from my side. Now, if you have some question, you can ask. I will wait for some more time. Or if not, you may leave. I will still wait if some more students join with their doubts.